The universe is not what you think it is. And the most dangerous part is, scientists are not even arguing about that anymore. They are slowly admitting it, because the deeper we go into matter, space, time, and reality itself, the less anything behaves like something solid, physical, or stable. What you see as reality is not reality. It is an experience built from something far more unstable than you were ever told. Matter is mostly empty. Time bends and breaks. Space is not empty at all, and observation itself changes what is real. So, the question is no longer what the universe is made of. The question is whether made of even applies at all, because nothing is holding reality together in the way your mind assumes. And once you understand even a small part of what physics is revealing, you start to realize something unsettling. Reality is not hiding secrets from you. It is behaving in a way that makes secrets unavoidable. And if that is true, then everything you think you know is only the surface of something much deeper that refuses to fully reveal itself. What you experience as solid matter is not solid in the way your senses suggest. When you touch a table, a wall, or even your own hand, your brain is interpreting a very strong interaction between atoms, not actual physical contact between solid objects. At the deepest level, everything you think of as solid is made of atoms, and atoms are not compact pieces of material packed tightly together. Each atom is made of a tiny nucleus at the center, containing protons and neutrons and electrons moving around it. But the distance between the nucleus and the electrons is enormous compared to their actual size. If you were to scale an atom up so that the nucleus was the size of a small ball, the electrons would be far away, and most of the space between them would contain nothing that resembles matter in the everyday sense. This means that almost all of the volume inside any object is not filled with stuff, but with empty space. The reason objects still feel solid is not because their atoms are physically pressed together like hard spheres, but because of the forces between them. When atoms come close, the electrons around them begin to interact through electromagnetic forces. These forces do not allow electrons to occupy the same state or position in a simple way, and this creates a strong resistance when you try to push objects into each other. That resistance is what your brain interprets as hardness, pressure, and solid contact. So when your hand touches a surface, there is no direct meeting of solid particles. Instead, there is a field-based interaction between the electrons in your skin and the electrons in the object. The feeling of touch is actually the result of electromagnetic repulsion and quantum restrictions that prevent atomic structures from overlapping. The sensation of firmness is therefore not evidence of solid material filling space, but evidence of forces preventing empty atomic structures from collapsing into one another. Even the atoms themselves are not dense physical objects in the classical sense. The nucleus, where most of the mass is concentrated, is extremely small compared to the atom as a whole. If you removed all the empty space inside atoms from every human being on Earth and compressed only the actual nuclear matter, the entire human population could, in theory, fit into a space far smaller than a single grain of sand. This does not mean matter is an illusion, but it does mean that solidness is not what it appears to be. It is a large-scale effect created by microscopic rules. What you call matter is therefore not a continuous substance, but a structured arrangement of energy fields that resist compression. The stability you experience is not because objects are full of material, but because the underlying rules of physics prevent their components from collapsing into the same space. In other words, solidity is not a property of substance itself, but a consequence of how particles interact when they are arranged in enormous numbers. This changes the way reality feels when you think about it carefully. A chair is not a single unified block of matter. It is a vast arrangement of mostly empty atomic structures, held in shape by forces that operate invisibly at the microscopic level. The reason it behaves like a stable object is because those forces are consistent and extremely strong at short distances, not because the chair is fundamentally solid in the way intuition suggests. So when physics says matter is mostly empty space, it is not describing a metaphor. It is describing a literal structure where the parts that carry mass occupy a tiny fraction of the total volume. The rest is not filled with hidden material, but with fields and interactions that define how those parts behave. What this ultimately means is that solidity is not a fundamental feature of reality. It is an emergent experience created by the way atomic forces organize large collections of particles. The world feels solid because the rules of interaction are reliable, not because reality is built from solid building blocks. What you normally call stillness is not something that exists in a literal physical sense. It is only an experience created by your perspective. When you sit quietly, when your body feels at rest, and when everything around you appears motionless, it feels as if nothing is moving. But at every level of physical reality inside you, motion never stops. Even when your body is not changing position in space, every part of it is active, shifting, vibrating, and continuously moving according to the rules of physics. Start with the most obvious level. Your body is made of organs, tissues, and cells. Even when you are perfectly still, your heart continues to pump blood through a complex network of vessels. Your lungs expand and contract, drawing air in and releasing it again. Your digestive system keeps working quietly in the background, breaking down substances and transporting nutrients. These processes alone show that stillness is already not complete, because life itself depends on constant internal movement. But if you go deeper than what biology shows you, the idea of stillness becomes even less accurate. Each cell in your body is filled with motion at a microscopic level. Molecules are constantly colliding, exchanging energy, and changing position. Water molecules inside your body are never fixed in place. They are always moving randomly due to thermal energy. Even in something that feels completely calm, there is a continuous internal activity driven by temperature and molecular interactions. The sensation of stillness does not come from the absence of motion, but from the balance of motions happening in all directions at once. If you go deeper again, beyond molecules, you reach atoms. Inside every atom, electrons are not sitting still around the nucleus like tiny planets frozen in orbit. In reality, they exist in quantum states that spread across regions of space, constantly influenced by energy levels and probability distributions. They do not have a single fixed position that can be pointed to at any given moment in the classical sense. Their behavior is described by continuous quantum activity, not rest. Even what seems like a stable structure is actually the result of ongoing motion governed by quantum rules. Inside the nucleus, protons and neutrons are also not static objects. They are made of quarks bound together by strong nuclear forces. And these quarks are in constant interaction, exchanging energy through force carriers called gluons. The inside of a nucleus is a highly dynamic environment where particles are never truly at rest. The stability of matter comes from balance, not stillness. If you move outward from the atomic scale to the scale of the Earth, the illusion of stillness becomes even more obvious. You are standing on a planet that is rotating at high speed. Even if you feel completely still in a room, you are being carried by the Earth's rotation around its axis. At the same time, the Earth is moving around the Sun at tens of kilometers per second. The Sun itself is orbiting the center of the galaxy, and the galaxy is moving through space as part of a larger cosmic structure. There is no absolute frame where everything is at rest. Motion is always relative, depending on what you compare it to. What this means is that the feeling of stillness is not a physical condition, but a limited interpretation. Your senses are tuned to detect changes that affect survival, not the full complexity of motion happening at all scales. If everything around you moves together at a similar speed, your body does not register that motion as movement. That is why you feel stationary, even while traveling through space at enormous speeds. At the smallest scale we currently understand, even the concept of absolute rest does not apply. Particles do not settle into a perfectly motionless state in the way classical intuition suggests. Instead, they exist in continuous activity defined by energy, interaction, and uncertainty. Even in a perfect vacuum, where no matter is present, fields still fluctuate and energy still exists in dynamic forms. There is no true absence of activity in the physical description of reality. So what you call stillness is actually a combination of synchronized motion and limited perception. It is the experience of moving together with everything around you in such a consistent way that no internal difference is noticeable. It is not the absence of movement, but the absence of detectable change relative to your frame of reference. Stillness is not something that exists independently in nature. It is something that emerges when motion becomes balanced, when changes cancel out from your point of view, and when your senses stop registering the underlying activity that never actually stops. What you experience as time is not something fixed, universal, or Adenakov for everything in the universe. It feels like a steady flow, always moving forward at the same rate, always ticking evenly from past to present to future. That feeling is extremely strong in everyday life because all of your senses, your routines, and your memory are built around it. But in physics, that sense of a single universal time is not how reality actually works. Time is not absolute. It changes depending on conditions you normally never think about, especially speed and gravity. To understand this, start with something simple. If two people are moving at different speeds, time does not pass for them in exactly the same way. A person traveling extremely fast compared to someone standing still will experience time more slowly relative to the stationary observer. From the outside, it would look like their clock is ticking more slowly. Their movements are slightly delayed, and even their biological processes are aging at a reduced rate compared to the person who is not moving as fast. This is not imagination or theory without evidence. It has been measured using extremely precise atomic clocks placed on airplanes and satellites. The difference is small at everyday speeds, but it is real and consistent. The reason this happens is not because time has a physical speed dial somewhere, but because space and time are deeply connected. In modern physics, they are treated as part of a single structure called spacetime. When you move faster through space, your motion through time then changes in a way that keeps the overall structure consistent. Instead of moving independently through space and time, you are always moving through a combined fabric of both. When more of your motion is used in space, less is available for time. That trade-off is what creates the effect of time slowing down at high speeds. Now add gravity to the picture. Time is also affected by gravitational fields. The stronger the gravity, the slower time passes compared to regions with weaker gravity. This means that time near a massive object, like a planet or a star, does not pass at the same rate as time far away from it. Even on Earth, this difference exists. A clock closer to sea level ticks slightly more slowly than a clock placed at a higher altitude because it is deeper in Earth's gravitational field. The difference is extremely small, but modern technology is precise enough to detect it. This happens because gravity is not just a force pulling objects together in a simple mechanical way. In Einstein's description of gravity, massive objects curve spacetime itself. That curvature affects not only how objects move through space, but also how time flows. The stronger the curvature, the more time is stretched or slowed. So time is not separate from gravity. It is influenced by it directly. What this means is that there is no single universal clock that the entire universe follows. Each location, each speed, and each gravitational condition has its own version of time. Two observers can both be correct about what they experience, even if their experiences do not match. One person might age slightly faster than another, simply because they spent their life in a weaker gravitational field, or moved at a different average speed. Over long periods, these differences become meaningful. Even satellites used for navigation systems like GPS has to account for this effect. Their onboard clocks tick at a different rate compared to clocks on Earth because they are both moving faster and experiencing weaker gravity. If these relativistic effects were not corrected, GPS systems would quickly become inaccurate. This shows that time differences are not just theoretical ideas. They are necessary for real-world technology to function correctly. At a deeper level, this breaks the idea that time is the same everywhere. Instead of a single universal flow, time becomes something local, shaped by conditions. It is not a background that stays fixed while everything else changes. It is part of the physical system itself, influenced by motion and gravity in measurable ways. So when you think about your own experience of time, what you are actually feeling is your personal path through space-time. It feels consistent because your environment is relatively stable. Your speed is not extreme, and Earth's gravity is fairly constant. But that stability is local, not universal. In other regions of the universe, near black holes, in high-speed motion, or across cosmic distances, time behaves differently enough that two observers could disagree significantly about how much time has passed. This leads to a deeper realization. Time is not a universal background ticking independently of everything else. It is something that depends on where you are, how fast you are moving, and how strongly you are influenced by gravity. Your experience of time is real, but it is not the full picture. It is one version of time among many, each shaped by the physical conditions of its environment. What you usually imagine as empty space is not actually empty. In everyday thinking, space feels like a kind of blank background where nothing exists unless you put something there, like objects floating in an empty room. But modern physics describes space in a very different way. Even when there is no matter present, no air, no light, and no particles in a region, that region is still not truly empty. It is filled with something more fundamental than particles. It is filled with quantum fields. To understand this, you need to shift the idea of what nothing means. In classical thinking, Nothing means the absence of everything. No objects, no energy, no activity. But in quantum physics, the vacuum is not a state of absolute nothingness. It is a physical state with structure, rules, and continuous activity. The vacuum is what remains when you remove all particles, but what remains is still something real. That something is a collection of fields that exist everywhere in space, even where no matter is present. A quantum field is not a material object like a gas or a liquid. It is more like a continuous presence that fills all of space, and every type of particle in the universe is connected to its own corresponding field. Electrons are excitations of the electron field. Photons are excitations of the electromagnetic field. Quarks are excitations of quark fields. In this picture, particles are not independent little balls moving through empty space. They are temporary disturbances in underlying fields that are always present everywhere. So when you remove all particles from a region, you are not left with nothing. You are left with the fields themselves, still existing in that region. These fields are not still or inactive. Even in what we call a perfect vacuum, they are constantly fluctuating. These fluctuations are not caused by external forces or leftover particles. They are built into the nature of quantum fields themselves. At extremely small scales, energy does not remain perfectly smooth or completely still. Instead, it shows random variations that appear and disappear continuously. These are called quantum fluctuations. They mean that even in the lowest possible energy state, space is never completely quiet. There is always a background level of activity, like a constant subtle vibration that never fully stops. This is not visible in everyday life, because it happens at scales far smaller than anything your senses can detect directly. But it has measurable effects in experiments. One way to understand this is to think about the vacuum not as empty space, but as a system that is always active at a hidden level. Even when there is no light or matter passing through a region, the fields in that region are still present, and their energy levels are never perfectly fixed. They fluctuate due to the rules of quantum mechanics, which allow for temporary changes in energy at very small scales. These fluctuations are not just theoretical ideas. They produce real physical effects. For example, in certain experiments, tiny forces appear between closely placed surfaces in a vacuum. This happens because the quantum fields between the surfaces behave differently than those outside them, creating a measurable pressure. This shows that the vacuum itself has properties that can influence matter, even when it seems like nothing is there. Another consequence of these fields is that particles can appear and disappear in very specific ways at microscopic scales. In high-energy environments, energy can briefly transform into particle-antiparticle pairs and then return back to energy again. This does not violate conservation laws because it happens within the limits allowed by quantum uncertainty. It shows that the vacuum is not a passive emptiness, but an active environment where energy and fields built in are constantly interacting. Even the idea of empty space in the universe, such as the vast regions between galaxies, is not truly empty. Those regions still contain quantum fields that extend everywhere. They may have extremely low density of particles, but the fields themselves are still present and still capable of fluctuation. This means that there is no point in the universe where the underlying structure of reality disappears. There is no location where physics stops existing. This changes the way you should think about space itself. Instead of being a blank container that holds objects, space is more like a layered system made of invisible fields that define what particles can exist and how they behave. The objects you see are not placed inside empty space like items in a box. They are expressions of the fields that fill that space. What feels like emptiness is actually a state where no stable particles are present, but the deeper structure is still active. The vacuum is not silent or inactive. It is a dynamic environment where fields constantly fluctuate, even when nothing material seems to be happening. So when physics says space is not empty, it is not adding invisible objects into an otherwise empty void. It is changing the definition of emptiness itself. Empty space is not nothing. It is a state of underlying fields that never fully stop, never fully disappear, and never become truly inactive. The universe is not built on emptiness. It is built on a continuous framework that exists everywhere, even where no matter exists. And what we call vacuum is simply the quietest possible state of something that is never truly still. Observation feels like something harmless. You look at a chair, and the chair does not change. You watch a river, and the river keeps flowing exactly as it was. You observe the sky, and the stars do not react to your gaze. In the classical world, observation is like opening a window in your mind. It lets information in, but it does not disturb what is outside. But at the quantum level, this idea breaks down completely. Here, seeing is not a neutral act. It is an interaction, and interaction means influence. The moment you try to measure a system at the smallest scales, you are no longer just watching it. You are physically affecting it in ways that cannot be removed or ignored. To understand this, imagine trying to observe something incredibly small, like an electron. An electron is not a tiny billiard ball sitting in one fixed place. It behaves more like a spread-out probability pattern, a cloud of possible locations where it might appear if you measure it. Before measurement, physics does not give you a single definite answer about where it is. It gives you a range of possibilities, all existing in a structured mathematical way. Now here is where the strange part begins. The moment you measure the electron, that range of possibility stops behaving like a spread-out cloud and becomes one definite outcome. It appears at one specific location with one specific value, not because it was always secretly there in that exact position, but because the act of measurement forces the system to settle into a single result. This is not just a limitation of instruments. It is not about our technology being too weak or too small. Even in perfect theoretical conditions, quantum systems behave this way. The act of measurement is built into the structure of the phenomenon itself. In other words, physics does not separate the system from the observer in the way classical intuition expects. At this level, observation means interaction through energy, particles, or fields. To see something, you must bounce something off it. To detect an electron, you might use photons, but those photons carry energy and momentum. When they interact with the electron, they change its state, so the act of measurement is not external. It becomes part of the system you are trying to understand. This creates a deep shift in how reality must be described. In classical thinking, objects have properties whether or not anyone looks at them. A stone is hard even when nobody touches it. A planet has a position even when nobody measures it. But quantum physics suggests that at the smallest scales, certain properties do not fully settle until they are measured. Before that, they exist in a state of possibility rather than fixed certainty. This does not mean reality is created by the mind, and it is important not to drift into that misunderstanding. The universe is not dependent on human awareness. Instead, What changes is the role of interaction. Any physical interaction that counts as a measurement, whether performed by a human, a machine, or the environment itself, forces a quantum system into a definite outcome. Even more surprising is that the type of measurement matters. Measuring one property can disturb another. If you try to precisely measure where a particle is, you lose precision in knowing how fast it is moving. If you measure its momentum more accurately, its position becomes less defined. This is not a flaw in instruments. It is a built-in feature of how quantum reality behaves, encoded in the mathematics of uncertainty. So at this level, reality is not a fixed picture waiting to be observed. It is a dynamic system where outcomes depend on what kind of interaction takes place. Different measurements reveal different aspects, but never all aspects at once with perfect clarity. The universe, at its smallest scale, does not offer a complete snapshot. It offers structured limitations on what can be known simultaneously. This leads to a deeper realization. What we call reality at the quantum level is not just about objects existing independently. It is about relationships between systems and the way those relationships resolve when interaction occurs. In this sense, observation is not passive at all. It is part of the physical process that shapes what becomes real in a measurable sense. And when you step back and look at the bigger picture, this changes how we think about certainty itself. It suggests that the universe does not always store all answers in a fixed form waiting to be revealed. Instead, some answers only take shape when the question is physically asked through measurement. So what feels like a simple act, looking at something, becomes, at the deepest level we understand, an event that participates in shaping the outcome. Reality is not just seen, it is engaging. When people hear the word particle, they usually imagine something simple and familiar. A tiny dot, a miniature ball, something that exists in one place at one time, moving along a clear path, just smaller than everything else. This mental image comes from the everyday world, where objects behave in stable, predictable ways. A grain of sand sits somewhere definite. A pebble has a position you can point to. Even invisible dust still exists in a specific location at any moment, even if you cannot see it. But when physics moves into the quantum level, this picture stops working. Not slightly, not as a small correction. It collapses completely. What replaces it is not another kind of tiny object, but something fundamentally different in nature, a structure of probabilities. At this scale, a particle is not described as being here or being there in a definite Instead, it is described by a mathematical structure that tells you where it might be found if you try to observe it. This structure is not ignorance in the usual sense. It is not that the particle secretly has a fixed position that we just do not know. Instead, the theory suggests that before measurement, the particle does not behave as a single localized object at all. It behaves like a spread of possibilities distributed across space. This spread is often called a wave-like probability distribution. But the word wave can be misleading if it makes you think of water or sound. There is no physical substance oscillating in space. What exists is a pattern that assigns different likelihoods to different outcomes. If you perform a measurement, you will not get a range of answers. You will get one outcome. But before that measurement happens, physics only gives you the structure of likelihoods. Imagine a situation where a particle is traveling toward a detection screen with two possible paths it could take. In classical thinking, it must choose one path, even if we do not know which one. But in quantum behavior, the particle is described as if it passes through a combination of possibilities at once, with each possibility contributing to the final probability of where it will be detected. The result you observe on the screen is a single point, but the pattern of many such detections builds up something that reflects the underlying probability structure, not a fixed trajectory. This is one of the most important shifts in modern physics. The idea that what we call a particle is not a miniature object traveling through space in a straight line. It is a system described by a wave of probabilities that evolves over time according to precise mathematical rules. These rules do not predict exact outcomes. They predict the structure of possible outcomes. Before measurement, the particle is not in a single defined state like a classical object. It exists in what physics calls a superposition of states. This does not mean it is physically split into pieces or duplicated in a literal sense. It means that its description includes multiple potential realities that coexist mathematically until interaction forces one of them to become actual in the observed result. The moment of measurement is where the transition happens. When the particle interacts with a detector, a screen, a field, or any system capable of recording information, the range of possibilities stops acting like a smooth spread and produces a single outcome. The result is definite: one position, one value, one detected event. But the path to that outcome is not a classical path of a single object moving through space. This creates a strange but consistent picture. Between measurements, the particle does not behave like something that has a hidden but definite route. It behaves like a continuously evolving probability structure. It is not traveling in the way a macroscopic object travels. Instead, it is evolving according to equations that describe how likelihoods shift, interfere, and combine over time. This interference is crucial. It shows that probabilities at the quantum level are not like simple odds in everyday life. In ordinary thinking, probabilities describe ignorance. If you flip a coin, it is either heads or tails, even if you do not know the result yet. But in quantum behavior, different possibilities can interact with each other before measurement. They can reinforce or cancel each other in ways that produce patterns that no classical system of hidden definite states can reproduce. This is why experiments, like the double-slit experiment, are so important. When particles like electrons are fired, one at a time, through two narrow openings, they do not behave like independent bullets passing through one slit or the other. Instead, over time, they build up an interference pattern on the detection screen. This pattern only makes sense if each electron is described as a probability structure passing through both possibilities in a combined way. Even though each final detection is a single localized point, the result is a layered reality. On one level, every measurement gives a clear, definite event. You always detect a particle in one place at one time. But on a deeper level, the distribution of many such events reveals that the underlying behavior is not the movement of individual classical objects, but the evolution of probability fields that govern where those events can occur. This is also where the idea of particle becomes misleading. A particle is not a little object that always exists in a fixed form. It is an excitation of an underlying quantum field, and that excitation is not localized in the classical sense until it is measured. Between interactions, it is better described as a spread of potential outcomes encoded in the structure of the field itself. So when we say particles do not behave like objects, we are not describing a small exception to normal physics. We are describing the fundamental rule at the smallest known scales. Object-like behavior is something that emerges only after repeated interactions, when probability structures collapse into stable, repeatable outcomes that can be treated as definite things in the macroscopic world. In this sense, the solid world we experience is built on top of a layer that is not solid in the classical sense at all. It is a network of evolving probabilities that only become definite when interaction forces a resolution. And what we call a particle is simply the most basic unit of that probabilistic structure, appearing as a single event when observed, but existing as a range of possibilities before that moment. So the deeper idea is not that particles are strange objects behaving unpredictably. The deeper idea is that at the foundation of reality, object is not the primary concept. Possibility is. And what we call matter is what those possibilities look like when they finally resolve into something definite through interaction. At the level of everyday life, reality feels stable and fully formed. Objects have clear shapes. Events have clear outcomes. If you drop a glass, it falls in a predictable way. If you switch on a light, the room becomes bright. If you walk across a floor, it stays solid beneath your feet. In this familiar world, things appear to exist in a settled condition, as if every detail of reality is already written and simply waiting to be experienced. This is the classical picture of the universe, and it works extremely well for large objects. But when we move into the quantum level, this sense of fixed certainty begins to dissolve, not gradually, not as a minor adjustment. It breaks down at its foundation. At the smallest scales of nature, physical systems do not behave like completed facts. They behave like open structures. Instead of having fully defined properties at all times, they exist in a state where multiple outcomes are possible at once, and no single outcomes is selected until an interaction occurs. This is what is meant by uncertainty in quantum physics. But the word uncertainty can be misleading if it suggests missing information, like a hidden answer we simply have not discovered yet. In classical thinking, uncertainty means ignorance. The result already exists. We just do not know it. Quantum physics suggests something more radical. It suggests that, before measurement, some properties do not have a single definite value in the classical sense at all. They exist as a structured range of possibilities. These possibilities are not random chaos. They follow precise mathematical rules. The evolution of a quantum system is not vague or arbitrary. It is governed by equations that determine how probabilities change over time. But those equations do not produce a single outcome. They produce a landscape of potential outcomes, each with a defined likelihood of becoming real when interaction happens. To understand this, imagine a situation where a particle is isolated, not being observed or disturbed. In classical thinking, we would assume it still has a definite position and velocity, even if we cannot measure them. But in quantum theory, the system is described by a state that includes all possible positions and velocities weighted in a precise way. It is not that the particle is hiding its true state. It is that the state itself is not a single fixed point. Now the key question becomes, what determines the final outcome we actually observe? The answer is interaction. When the quantum system interacts with a measurement device, another particle, or even the surrounding environment, the range of possibilities stops evolving as a spread and resolves into a single event. One outcome becomes real in the context of that interaction, while the other possibilities no longer appear in the recorded result. This process is often described as a measurement. but that word can create confusion. It sounds like a human action, something requiring an observer. In reality, it does not depend on consciousness or awareness. Any physical interaction that transfers information between systems can act as a measurement. A detector clicking, a photon scattering off an electron, or even random environmental interference can all force a quantum system into a definite state. What changes during this process is not just what we know, but what can be consistently recorded as a fact in the physical world. Before interaction, the system is not locked into a single outcome. After interaction, it is. This transition is one of the deepest features of quantum physics and one of the least intuitive. It is important to understand that this does not mean reality is unstable in a chaotic sense. The uncertainty is not a disorder. It is structured without final selection. The system evolves in a predictable way, but the final outcome remains open until interaction selects one possibility from the allowed range. This is very different from how classical systems behave. In classical physics, if you know all initial conditions exactly, you can in principle predict the future with complete certainty. The system evolves along a single path. There is no branching of possibilities. Quantum systems do not behave this way. Even with complete knowledge of the quantum state, you can only predict probabilities, not definite outcomes. This leads to a shift in how we think about reality itself. Instead of being a fixed chain of events, reality at its smallest level looks more like a continuously evolving field of potential outcomes. These outcomes do not all become real simultaneously. They remain in a state of unresolved structure until interaction forces a selection. One way to think about this is to imagine reality as something that is not fully written in advance. Instead, it is partially open, with rules that define what can happen, but not always what will happen. The rules define boundaries and likelihoods, but the actual event emerges only when a physical interaction takes place. This is not a gap in our knowledge that future science will simply fill in with missing details. It is a structural feature of the theory that has been confirmed repeatedly through experiments. No matter how precise our measurements become, the uncertainty does not disappear. It is built into the way nature behaves at this scale. Experiments such as those involving small particles passing through barriers or being detected one at a time show this clearly. Each individual event is unpredictable. You cannot say exactly where a single particle will appear before it is measured. But over many repetitions, a pattern emerges that matches the mathematical probability distribution predicted by quantum theory. This combination of unpredictability at the individual level and precision at the statistical level is one of the defining features of quantum reality. So what does it mean to say that reality is not fixed? It means that at the smallest scale, nature does not assign a single definite outcome to every event in advance. Instead, it allows a set of possible outcomes to exist in a structured relationship. And only when interaction occurs does one of those possibilities become an actual recorded fact. This creates a layered view of existence. On one layer, there is the evolving structure of possibilities, constantly shifting according to quantum rules. On another layer, there is the world of definite events that we observe, where outcomes appear fixed and irreversible. Our everyday experience belongs to this second layer, but it is built on top of the first. The transition between these layers is not random in the sense of pure chaos. It is probabilistic in a controlled and mathematically consistent way. That is why quantum physics can make extremely accurate predictions about large numbers of events, even though it cannot determine individual outcomes with certainty. So the core idea of this lesson is not simply that things are uncertain. It is that certainty itself is not fundamental at the smallest scale. It is something that emerges from interaction. Reality is not a pre-written script, unfolding exactly the same way regardless of observation. It is a structured system of possibilities that becomes definite only when it is physically engaged, and once this idea is understood, it changes the way we interpret everything else built on top of it, because it suggests that what we call facts are not always pre-existing truths waiting to be discovered, but outcomes that become fixed only when the universe is forced to choose between possibilities through interaction. Gravity is the most familiar force in human experience, and at the same time, one of the most mysterious when examined closely enough. It is the reason objects fall when dropped, the reason planets stay in orbit, the reason stars form from clouds of gas, and the reason galaxies hold together across distances so vast that light itself takes tens of thousands of years to cross them. Every moment of physical existence is shaped by it, even when we are not consciously aware of it. And yet, despite this constant presence, gravity is strangely different from the other fundamental forces of nature. Electromagnetism has a clear quantum description in terms of particles and fields. The strong and weak nuclear forces are described within a well-tested framework that predicts particle interactions with extraordinary precision. Gravity, however, behaves differently when we try to fit it into the same quantum structure. It works flawlessly in large-scale physics, but resists full integration at the smallest scales. At the macroscopic level, gravity is described with remarkable accuracy by Einstein's general theory of relativity. In this framework, gravity is not treated as a force in the traditional sense. Instead, it is the curvature of spacetime itself. Massive objects like planets, stars, and galaxies distort the geometry of space and time around them, and this distortion determines how other objects move. In this view, a falling object is not being pulled in the classical sense. It is simply following the natural curves of space-time geometry. This description has been tested repeatedly. It explains the orbit of Mercury, the bending of light around massive galaxies, the time dilation experienced near black holes, and even the ripples in space-time detected as gravitational waves when massive objects collide. On these scales, gravity is not just accurate. It is one of the most precisely confirmed theories in all of physics. But when physicists try to push this description deeper, into the quantum level where particles and fields dominate, something begins to break. The smooth geometric picture of space-time starts to conflict with the probabilistic and discrete nature of quantum mechanics. At small enough scales, space-time itself is expected to fluctuate. But general relativity does not naturally include these fluctuations. It assumes a smooth background, not a quantum one. This is where the central mystery begins. We can describe how gravity behaves extremely well. We can calculate its effects, predict its influence, and observe its consequences across the universe. But we do not yet have a complete understanding of what gravity is in the same fundamental sense that we understand other forces. One of the biggest challenges is that gravity is not easily quantized. When physicists attempt to treat gravity like the other forces, by introducing a particle called the graviton as a carrier of gravitational interaction, the mathematics becomes unstable at very high energies. The equations produce infinities that cannot be easily removed without additional structure. This suggests that our current frameworks are incomplete rather than incorrect, but it also shows that gravity may not be a force in the same way as the others. Another strange feature of gravity is its universality. Every form of energy, not just mass, contributes to gravitational effects. Light, heat, pressure, and even the energy of empty space itself all interact with gravity. This makes gravity different from forces like electromagnetism, which depend on specific properties, such as electric charge. Gravity responds to everything, which makes it both incredibly simple in behavior and incredibly difficult in underlying explanation. There is also the issue of scale. Gravity is extremely weak compared to other forces. A small magnet can overcome the entire gravitational pull of the Earth on a paperclip, and yet, over large distances and massive objects, gravity dominates everything else. It is the architect of cosmic structure. It shapes the universe at the largest scales while appearing almost negligible at the smallest. This dual nature is part of what makes gravity so puzzling. It is both simple and dominant on one hand, and weak and elusive on the other. It behaves like geometry in Einstein's description, but like a force mediated by particles in quantum approaches. Neither picture is complete on its own when pushed to the extremes of scale. Some modern theories suggest that gravity might not be fundamental at all. Instead, it could emerge from deeper physical processes. In these ideas, spacetime itself might arise from more basic information like structures, and gravity would be a large-scale effect of how that information is organized. In this view, gravity is not something that exists at the deepest level, but something that appears when many underlying elements interact in a specific way. Other approaches, such as string theory and loop quantum gravity, attempt to describe gravity within a unified framework of quantum physics. These theories propose that space-time may have a discrete structure at extremely small scales, far beyond current experimental reach. In loop quantum gravity, for example, space itself is composed of quantized building blocks, and gravitational effects arise from the relationships between them. In string theory, gravity emerges naturally from the vibrations of fundamental strings, which also give rise to all other particles. Despite these promising directions, no single theory has yet been confirmed experimentally as the correct description of quantum gravity. This leaves us in a unique position in physics. We have a theory of gravity that works perfectly at large scales, and we have quantum theories that work perfectly at small scales. But we do not yet have a fully unified picture that combines them without contradictions. What makes this even more intriguing is that gravity is not just another force to be explained. It is the structure of spacetime itself in our current understanding. This means that solving gravity is not just about adding another particle or interaction to the list. It is about understanding the nature of space and time at their most fundamental level. This is why gravity feels both familiar and deeply unknown. We experience its effects constantly. It shapes every movement, every orbit, every structure in the universe. And yet, when we ask what it fundamentally is, the answer becomes uncertain. We can describe its behavior with extreme accuracy, but its underlying essence remains one of the biggest open questions in science. So gravity stands in a unique position. It is the most visible invisible force. It is perfectly described in practice, but incomplete in principle. It connects everything in the universe, from falling objects on Earth to the motion of entire galaxies, and yet it resists full explanation in the language of quantum physics. Gravity works without exception. It never fails in prediction, never breaks in observation, and never contradicts itself in known experiments. But at its deepest level, it still does not reveal what it truly is. It only shows what it does. When we look up at the night sky, it feels like we are seeing the universe itself. Stars shine clearly. Planets reflect light. Galaxies appear as glowing structures stretching across space. Even through telescopes, what we observe seems like a complete picture of cosmic reality. But this impression is deeply misleading. What we see is only a small fragment of what actually exists. The visible universe, everything that emits, reflects, or absorbs light, represents only a minor portion of the total content of reality. The rest does not interact with light in a meaningful way, which means it cannot be seen through conventional observation. It does not glow, it does not reflect, and it does not block radiation in the way ordinary matter does. And yet, its presence is not hypothetical. It is inferred through its effects on the structure and behavior of the universe. This hidden component is divided into two major parts: dark matter and dark energy. Together, they dominate the universe in terms of total composition. Ordinary matter, the kind that makes up stars, planets, and human beings, is actually a small fraction of everything that exists. The majority is something we cannot directly observe. Dark matter is the first part of this invisible structure. It does not emit light, and it does not interact with electromagnetic radiation, which is why it cannot be seen with telescopes. But it does interact through gravity. We know it exists because of the way galaxies behave. When astronomers measure how fast stars rotate around the centers of galaxies, they find something unexpected. The outer regions of galaxies are moving too fast to be held together by visible matter alone. According to classical gravitational calculations, galaxies should fly apart if only the observable mass were present. The stars at the edges should not have enough gravitational pull keeping them in orbit. But they do not drift away. Instead, they remain tightly bound, moving in ways that suggest there is far more mass present than what we can see. This missing mass is what we call dark matter. Further evidence comes from gravitational lensing. When light from distant galaxies passes near massive objects, its path bends due to gravity. By studying how light bends in space, scientists can map the distribution of mass in the universe. These maps consist of Morse mass than can be accounted for by visible matter alone. The extra mass forms large-scale structures that shape the way galaxies cluster and move. Dark matter does not behave like normal matter. It does not form atoms, does not emit radiation, and does not interact with itself in the same way ordinary particles do. It appears to pass through everything without resistance, except through gravitational influence. It acts like an invisible framework, holding galaxies and clusters together, shaping the cosmic structure without ever being directly observed. The second major component of the invisible universe is even more mysterious: dark energy. Unlike dark matter, which pulls things together through gravity, dark energy appears to drive the expansion of the universe itself. It is responsible for the fact that the universe is not just expanding, but expanding at an accelerating rate. This discovery came from observations of distant supernovae. When scientists measured the brightness and distance of these exploding stars, they expected to see evidence of a slowing expansion due to gravitational attraction. Instead, they found the opposite. The expansion of the universe is speeding up over time, as if some hidden force is pushing space apart. Dark energy is not understood in the same way as matter or force fields. It is not localized in objects or particles. It appears to be a property of space itself. As space expands, more dark energy seems to appear, maintaining a constant density throughout the universe. This behavior is unlike any known form of matter or energy in classical physics. Together, dark matter and dark energy dominate the structure and fate of the universe. Ordinary matter, everything we can see and touch, makes up only a small percentage of the total cosmic content. The rest is hidden, not because it is rare or distant, but because it does not interact with light in a way that allows direct detection. This creates a strange situation in science. We are able to map, measure, and predict the behavior of something we cannot directly observe. We infer its presence through gravitational effects, large-scale cosmic structure, and the expansion history of the universe. It is as if we are studying the shape of an invisible object by watching how it moves everything around it. Dark matter and dark energy are not small corrections to our understanding of the universe. They represent a fundamental gap in our knowledge. We do not yet know what dark matter is made of. It could be a new type of particle that has not yet been detected, or it could require a deeper revision of gravitational theory itself. Similarly, dark energy has no confirmed physical explanation. It may be related to vacuum energy, quantum fields, or something even more fundamental that we have not yet conceptualized properly. What makes this even more profound is that the universe behaves consistently, as if these unseen components are real. The equations that include dark matter and dark energy match observations with remarkable precision. Without them, our models of the cosmos fail to describe reality accurately. With them, the large-scale structure of the universe becomes understandable. This leads to a striking realization. Most of what exists is not directly accessible to human senses or direct instruments. We do not experience dark matter or dark energy in daily life. We do not see them, touch them, or interact with them in any direct way, and yet they shape everything we do experience. From the motion of galaxies to the evolution of the entire universe. The universe is not fully visible even in principle. A large part of its structure is hidden not behind distance or time, but behind the limits of interaction. If something does not emit or reflect light, and only interacts gravitationally or through unknown mechanisms, it becomes invisible to traditional observation. And yet, it still plays a central role in the architecture of reality. So the lesson here is not just that there are things we cannot see. It is that visibility is not a reliable measure of existence. The universe contains vast structures that remain permanently outside direct detection, and we only know them through indirect evidence and mathematical consistency. This changes how we think about reality itself. What we call the universe is not just the collection of things we can observe. It is a much larger system, most of which is hidden from direct view, yet essential to everything we do see. And as our instruments become more precise, we are not just seeing more of the same universe. We are uncovering the fact that most of it was never visible to begin with. One of the most surprising discoveries in modern cosmology is that the universe is not only expanding, but that this expansion is speeding up. At first, this idea sounds like it should not make sense. If you imagine the universe as something that began with a massive outward expansion, it would be natural to expect that gravity, acting on all matter, would slowly pull everything back and cause the expansion to decelerate over time. For a long time, scientists believed exactly that. The expectation was simple. After the initial expansion from the Big Bang, gravity should act like a braking force. Galaxies should gradually slow their separation. The expansion might continue, but at a decreasing rate. The universe should be losing energy to gravity as it stretches outward. But observations showed something completely different. When astronomers began measuring distant supernovae, extremely bright stellar explosions used as reference points for measuring cosmic distances, they noticed a strange pattern. Light from very distant supernovae was dimmer than expected, not because of dust or measurement error, but because those objects were farther away than they should have been if the universe's expansion was slowing down. The only consistent explanation was that the expansion of the universe was not slowing. It was speeding up. This result was unexpected enough that it changed the entire direction of cosmology. It suggested that something is pushing space itself apart, overcoming the attractive force of gravity on the largest scales. Not just once, not temporarily, but continuously over billions of years. This accelerating expansion is now one of the most important observations in physics. It has been confirmed through multiple independent methods, including measurements of the cosmic microwave background, galaxy clustering, and large-scale structure surveys. All of them point to the same conclusion. The rate at which space expands is increasing with time. But here is the central problem. We can measure this acceleration very precisely. We can describe how it behaves. We can include it in our mathematical models of the universe. What we cannot do is fully explain what causes it. The unknown driver behind this acceleration is often labeled dark energy, but that label is more of a placeholder than a real explanation. It names the effect without revealing the mechanism. It tells us that something is present, but not what it is or how it works. One possibility is that dark energy is related to the energy of empty space itself. In quantum physics, even a perfect vacuum is not truly empty. It contains fluctuations of fields that exist everywhere in space. These fluctuations might produce a small but persistent energy that does not dilute as the universe expands. If this energy is real, it would act like a constant pressure, push space apart uniformly in all directions. Another possibility is that gravity behaves differently on the largest scales than we currently understand. General relativity has been tested extremely well in solar systems and galaxies, but the accelerating expansion of the universe operates at a scale far beyond those environments. It is possible that the equations need modification when applied across billions of light years. There are also more speculative ideas suggesting that dark energy could be dynamic, changing over time rather than remaining constant. In some models, it is linked to new fields that evolve as the universe expands, gradually influencing the rate of expansion in ways we have not yet fully mapped. Despite these possibilities, none of them has been confirmed. Each explanation fits some aspects of the data, but none has emerged as the definitive answer. This is what makes the situation so unusual. We are not dealing with a small gap in understanding or a missing detail in an otherwise complete theory. We are dealing with a fundamental feature of the universe whose origin remains unknown. What makes this even more striking is the scale of what is being described. This is not a local phenomenon. It is not something happening inside galaxies or within clusters of matter. It is happening to space itself, everywhere, simultaneously. Every region of the universe is participating in this expansion, and every moment of cosmic time shows that the rate is increasing. This means that the structure of the universe is not static. It is not just expanding like a balloon that was inflated once in the past. It is expanding in a way that continues to gain speed, as if some underlying property of space is driving it apart more strongly as time passes. And yet, despite knowing all of this observationally, we still do not know the underlying cause. We can describe the effect with equations. We can match the data with models. We can measure the acceleration to high precision. But the deeper reason remains hidden. This creates a strange situation in physics. It is one of the few areas where the most precise measurements we can make still leave us without a fundamental explanation. We know what the universe is doing. We do not know why it is doing it in this particular way. So this lesson is not just about expansion. It is about the limits of explanation at cosmic scale. It shows that even when a phenomenon is observed clearly, repeatedly, and with high accuracy, the underlying cause can still remain out of reach. The universe is expanding faster over time, but the mechanism behind that acceleration is still one of the deepest open questions in science. When you look at a galaxy from far away, it appears like a massive rotating system where billions of stars orbit a central point in a slow, organized pattern. At first glance, it feels like a simple application of gravity. More mass in the center pulls everything inward, and the outer stars should move more slowly than the inner ones, just like planets in a solar system. That is the intuitive expectation, the kind of prediction you would make if all the mass you could see was all the mass that existed. But when scientists actually measure the motion of galaxies, something unexpected appears. The outer regions of many galaxies do not slow down the way they should. Instead, they move at speeds that are far too high compared to the amount of visible matter present. If only the stars, gas, and dust we can see were responsible for the gravity, those outer stars should be drifting away or moving much more slowly. Yet they stay bound, moving in stable orbits as if something invisible is adding extra gravitational influence. This mismatch between expected motion and observed motion is not a small error in measurement. It is consistent, repeatable, and seen across countless galaxies. No matter where we look, the same pattern appears. Visible matter alone is not enough to explain how fast galaxies rotate. It is as if every galaxy is embedded in a much larger structure that we cannot directly observe, but whose gravitational effects are clearly present in the motion of everything inside it. This unseen influence is what scientists refer to when they talk about dark matter. It is not dark in the sense of being black or empty. It is dark because it does not interact with light. It does not emit, absorb, or reflect radiation in a way that telescopes can detect. We cannot photograph it. We cannot directly isolate it. We only know it exists because of what it does to visible matter, especially in the rotation of galaxies. The idea of unseen mass-shaping motion forces a deeper shift in how we think about reality. It means that what we see is not a complete map of what exists. The stars and glowing gas clouds that form the beautiful spiral arms of galaxies are only a fraction of the total structure. The rest is hidden, forming a kind of invisible framework that holds everything together through gravity alone. This hidden framework is not evenly distributed in the way normal matter is. It forms large, diffuse halos that extend far beyond the visible edges of galaxies. These halos are not made of atoms like the matter we know. They behave differently, interact differently, and remain invisible to every form of electromagnetic observation we have developed so far. Yet their gravitational presence is so strong that without them, galaxies would not maintain their structure at all. In fact, if you remove this unseen component from our calculations, the entire architecture of galaxies begins to break down. Spiral arms would lose their coherence. Stars at the edges would escape into space. The stable, long-lived structures we observe across the universe would not have enough binding force to exist in their current form. Something essential would be missing, not in theory, but in reality. What makes this even more striking is that this pattern is not unique to a single galaxy. It appears everywhere, from small dwarf galaxies to massive spiral galaxies. The same inconsistency between visible mass and rotational speed repeats itself. This repetition across such different environments suggests that whatever is causing it is not a local anomaly, but a fundamental part of how the universe is structured. Scientists have tested many possibilities to explain this behavior. Some have explored modifications to gravity itself, suggesting that perhaps our understanding of gravitational laws changes at large scales. Others have focused on the idea of new unseen particles that do not interact with light but still have mass. While different models exist, the one thing all approaches agree on is that the visible universe is incomplete on its own. The motion of galaxies becomes, in this sense, a kind of silent evidence. It is the universe revealing that what we perceive through light is only a partial translation of something far deeper. The glowing stars are like surface ripples on an ocean whose true depth remains hidden beneath layers we cannot directly observe. This realization does not make galaxies less real or less beautiful. Instead, it expands the meaning of what they are. A galaxy is no longer just a collection of stars held together by visible gravity. It becomes a structure shaped by both seen and unseen components, where the invisible plays a decisive role in defining the motion, stability, and long-term evolution of everything within it. And so, when we say galaxies rotate in ways that suggest unseen mass, we are not just describing a technical anomaly in astrophysics. We are pointing toward a deeper truth, that the universe is not fully transparent to observation, and that some of its most important ingredients reveal themselves only through their influence, not their appearance. When we look at the universe carefully, one of the most surprising patterns is not just what we discover, but how we are able to discover it. Across every level of reality, from the smallest particles to the largest cosmic structures, there are rules that consistently work. These rules allow us to predict, calculate, and build models that match what we observe. And yet, even when these rules work with extraordinary precision, there is still a gap between using them and truly understanding why they exist in the form they do. At the simplest level, think about everyday physics. Gravity allows us to calculate how objects fall. Motion equations let us predict how things move when forces act on them. Electricity and magnetism let us design devices that power cities. These rules are not vague ideas. They are extremely accurate tools. They let engineers build bridges, satellites, computers, and medical equipment with reliability that depends on precise mathematical consistency. If the rules were even slightly different, much of modern technology would fail instantly. But even at this level, something important is hidden in plain sight. We can describe how these rules behave, but we cannot fully explain why reality follows these exact rules instead of slightly different ones. Why does gravity have the strength it has? Why do electromagnetic forces behave in the specific way they do? Why are the constants of nature tuned to values that allow stable atoms, long-lived stars, and structured matter. We can measure them with extreme precision, but we cannot derive them from something more fundamental in a complete way. As we move deeper into physics, this pattern becomes even clearer. In classical mechanics, the laws of motion are elegant and consistent. In quantum mechanics, the rules become probabilistic, but still highly predictive. Particles behave in ways that can be calculated with astonishing accuracy. Yet, their underlying nature remains difficult to visualize. We can write equations that match experiments perfectly, but the meaning behind those equations often resists simple interpretation. For example, quantum theory tells us how particles behave when observed, but it does not easily explain what those particles are doing when they are not being measured. The mathematical structure works flawlessly in practice, yet the picture behind it is not fully settled. Different interpretations exist, each trying to make sense of the same successful rules. But none can be confirmed as the single, complete description of reality. When we move to the scale of atoms and chemistry, the same pattern continues. The periodic table is structured by quantum rules that determine how electrons arrange themselves around nuclei. These rules explain why elements behave the way they do, why chemical bonds form, and why matter has the properties it does. But again, we are using the rules without fully uncovering why the rules have exactly this structure. The system is internally consistent and experimentally verified, but conceptually deeper questions remain open. At the scale of stars and galaxies, gravity becomes the dominant rule. It governs how gas clouds collapse, how stars form, how galaxies rotate, and how large-scale cosmic structures evolve. The equations describing gravity are among the most successful in all of science. They predict planetary motion, black hole behavior, and even the expansion of the universe with remarkable accuracy. Yet gravity itself remains partially mysterious. We know how to use it. We know how it behaves, but we do not yet know how it fits into a complete framework with quantum mechanics at the deepest level. This creates a situation where physics is both powerful and incomplete at the same time. It gives us tools that work across enormous scales, but it does not always provide final explanations for why those tools exist. The rules function like a language we have learned to speak fluently, even though we do not fully understand the origin of the grammar behind it. One of the most striking aspects of this situation is how consistent it is. It is not just one area of physics that has this gap between usability and full explanation. It appears everywhere. In thermodynamics, we can predict how heat flows, but the microscopic origin of entropy leads to deep questions about time and disorder. In particle physics, we can calculate interactions with extreme precision, but the reason for the specific particle spectrum remains open. In cosmology, we can model the evolution of the universe, but the origin of initial consciousness is still unknown. This pattern suggests something important about the nature of scientific understanding itself. Science does not begin with complete explanations and then apply them. Instead, it begins with rules that work, and then gradually tries to uncover why they work. The success of the rules comes first. The deeper explanation often comes later, if it comes at all. At every scale of reality, we are therefore standing in a similar position. We are users of a system whose behavior is consistent enough to navigate and predict, but whose ultimate foundation is still partially hidden. We can move through it, build within it, and describe it with increasing accuracy. But we do not yet hold the final reason why it is structured the way it is. This is not a weakness of science. It is actually what allows science to progress. If everything were already fully explained, there would be nothing left to discover. The gap between prediction and understanding is not a failure. It is the space where new physics, new mathematics, and new insights emerge. So when we say every scale of reality depends on rules we can use, but not fully explain, we are describing something very precise about the nature of knowledge itself. We are living inside a system where the instructions are clear enough to follow, but the origin of those instructions is still unfolding. And as we continue to explore deeper layers of reality, the same pattern keeps repeating. The rules become more powerful, more accurate, and more universal. But the question of why those rules exist in exactly that form remains open, waiting at the edge of what we currently understand. One of the most important and least discussed features of modern science is this strange separation between what we can predict and what we can truly explain. Physics is extremely powerful when it comes to calculating outcomes. It can tell us where a planet will be years from now, how a beam of light will bend around a massive star, how an electron will behave in a magnetic field, or how a star will collapse after exhausting its fuel. In terms of prediction, the success is almost unreal. The equations work with a level of accuracy that often reaches many decimal places, matching experiments and observations across enormous ranges of scale. But when we move from prediction to interpretation, something very different happens. The same equations that produce precise answers do not always provide a clear picture of what is really happening. They tell us what will be measured, but not always what exists between measurements. They tell us how systems evolve mathematically, but not always what that evolution's seen in physical or intuitive terms. This gap becomes especially visible in quantum physics. The mathematical framework of quantum mechanics is one of the most successful theories ever created. It can predict the results of experiments with extraordinary precision. If you calculate the probability of finding a particle in a certain place, the answer matches reality with astonishing accuracy. If you model how atoms interact with light, the predictions align with observations almost perfectly. Every technology built on quantum physics, from lasers to semiconductors to MRI machines, depends on this predictive success. Yet despite this success, the interpretation of what the theory actually means remains deeply unsettled. The equations do not clearly tell us what an electron is doing when it is not being measured. They describe probabilities, wave functions, and outcomes. But the meaning of those probabilities is still debated. Is the particle in many states at once? Is reality splitting into branches? Or is there some hidden structure we have not yet discovered? Different interpretations exist, each trying to make sense of the same mathematical framework. But none can claim final authority. This situation creates a kind of tension. On one side, the theory works perfectly in practice. On the other hand, our understanding of what the theory is describing remains incomplete. It is as if we have a map that is perfectly accurate in showing where everything is, but we are not fully sure what the map represents. This pattern is not limited to quantum physics. In classical physics, the situation appears simpler, but the same underlying divide still exists. Newton's laws allow us to predict motion with great accuracy. We can calculate how objects move under gravity, how forces affect acceleration, and how systems evolve over time. These predictions are reliable and form the foundation of engineering and astronomy. Even in this classical framework, interpretation raises deeper questions. What is force, fundamentally? Is gravity a force, or is it the curvature of spacetime? Why does mass produce attraction in the way it does? Newton's equations work without answering these questions. They describe the behavior of objects, but not the underlying reason why that behavior takes the form it does. As Einstein introduced general relativity, the predictive power increased in certain domains, especially in extreme gravitational conditions. The theory could predict the bending of light, the orbit of Mercury, the existence of black holes, and the expansion of the universe. Again, the match between prediction and observation was remarkable. But even here, interpretation became more complex. Gravity was no longer a force in the traditional sense, but a curvature of spacetime. Yet what spacetime itself is remains a subject of ongoing investigation. The same divide appears in thermodynamics. We can predict how heat flows from hot objects to cold ones. We can calculate entropy changes, energy distributions, and equilibrium states with high precision. These predictions are essential for chemistry, engineering, and cosmology. But the interpretation of entropy, especially its connection to time and information, is still not fully settled. We can use the equations effectively, but the deeper meaning of why disorder increases in the way it does continues to raise questions. Even in statistical physics, where large systems are described using probabilities, we see the same structure. The predictions are accurate because they do not require knowledge of every microscopic detail. Yet the interpretation of probability itself becomes subtle. Is probability a reflection of ignorance, or is it a fundamental feature of reality? The equations remain silent on this philosophical question, even though they work perfectly in practice. At larger scales in cosmology, the same pattern becomes even more striking. Models of the universe's expansion, structure formation, and cosmic background radiation provide predictions that match observations with impressive accuracy. We can simulate how galaxies form, how matter clusters, and how the universe evolves over billions of years. But when we try to interpret what the universe is, at the deepest level, questions remain open. What is dark matter made of? What is dark energy? What caused the initial conditions of the Big Bang? The predictive framework works, but the interpretation is still under construction. This separation between prediction and interpretation is not a flaw in physics. It is actually one of its defining features. Physics prioritizes measurable outcomes. It focuses on what can be tested, repeated, and verified. As long as the predictions match reality, the theory is considered successful. Interpretation, on the other hand, is not always required for practical success. This is why multiple interpretations can coexist for the same mathematical theory without affecting its experimental validity. This also means that our intuitive understanding of reality often lags behind our technical ability to calculate it. We can compute the behavior of systems that we cannot fully visualize. We can predict outcomes in regimes where our conceptual models become unclear. In some cases, we even rely on mathematical structures that have no simple physical analogy at all, yet still produce correct results. This leads to a kind of scientific duality. On one side, there is operational physics, the part that produces predictions and technological applications. On the other side, there is interpretive physics, the attempt to understand what those predictions mean in terms of reality itself. Both are important, but they do not always progress us at the same pace. Prediction advances faster than interpretation. New experiments refine equations before we fully understand their implications. New data improves accuracy before conceptual clarity is achieved. This is why modern physics can feel simultaneously complete and incomplete. It is complete in its ability to predict outcomes, but incomplete in its ability to provide a single unified picture of what those outcomes represent. So, when we say physics works perfectly in prediction, but often fails in interpretation, we are describing a structural feature of scientific knowledge. It reflects the difference between knowing how something behaves and knowing what that behavior fundamentally means. And across every major area of physics, this gap remains one of the most important and ongoing frontiers of understanding. At the surface level of everyday life, reality feels simple to understand without needing equations. You see objects, you feel forces, you notice movement, and your mind builds an intuitive picture of how things work. If you push a chair, it moves. If you drop something, it falls. If you throw a ball, it follows a curved path and eventually stops. These experiences create a natural sense of physics that is built from direct observation and repeated experience. In this world, intuition feels reliable because it is shaped by constant interaction with the same scale of reality. But as we move beyond this everyday layer and begin to explore deeper levels of nature, that intuitive understanding starts to lose its strength. The rules of reality no longer match the way things feel in daily life. Instead, they begin to follow patterns that are not obvious to the senses and cannot be fully grasped through imagination alone. At this point, mathematics starts to take over as the main language of description. In classical physics, this transition is already visible. Newton's laws replace intuition with precise equations. Instead of saying objects naturally slow down, we describe friction, force, and acceleration. Instead of saying planets feel the sun's pull, we describe gravitational attraction using mathematical relationships. Even though these ideas can still be visualized, they already require a structured mathematical framework to be fully accurate. Intuition alone is no longer enough to predict outcomes with precision. As physics progresses further into electromagnetism, the role of mathematics becomes even more dominant. Electric and magnetic fields cannot be directly seen or touched, yet they follow strict mathematical laws that allow us to predict their behavior with extreme accuracy. The equations describe how fields interact, how charges move, and how waves propagate through space. At this stage, intuition begins to struggle. It is no longer easy to picture what is happening without relying on mathematical symbols to guide understanding. When we reach quantum physics, the shift becomes even more dramatic. The behavior of particles at this scale does not resemble anything in everyday experience. Electrons do not move like tiny planets, and light does not behave like simple waves or particles in the classical sense. Instead, everything is described through mathematical objects such as wave functions, operators, and probability amplitudes. These are not things that can be easily visualized. They are abstract structures that exist primarily within the language of mathematics. In quantum theory, the equations do not describe definite paths or clear physical trajectories. Instead, they describe probabilities of outcomes. A particle is not assigned a single fixed position before measurement. Instead, it is represented by a mathematical distribution that contains all possible outcomes at once. This is where intuition begins to break down most clearly. The mind wants to imagine something solid and definite, but mathematics describes something that is spread across possibilities until an interaction forces a specific result. As we go deeper into modern physics, especially into quantum field theory, Even the idea of particles becomes less fundamental. Fields become the primary objects, and particles are seen as excitations of those fields. These fields are not physical substances in the traditional sense. They are mathematical entities defined at every point in space and time, governed by equations that describe how they evolve and interact. The reality we observe emerges from these mathematical structures rather than existing independently of them. Physical intuition becomes increasingly unreliable. There is no simple mental picture that can fully capture what the equations are describing. Even physicists rely heavily on mathematical formalism rather than visualization. The equations are not just tools for calculation. They become the only consistent way to represent what is happening. When we move into general relativity, the situation becomes even more abstract. Space and time themselves are no longer fixed backgrounds. They become dynamic structures described by geometry. Gravity is not treated as a force in the traditional sense, but as the curvature of space-time. This curvature is expressed through tensors and differential equations that describe how geometry changes in response to mass and energy. At this point, even space itself becomes something that is defined mathematically rather than intuitively. It is difficult to build a mental picture of curved space-time without relying on mathematical language. Diagrams and analogies can help, but they are only partial representations. The true structure of the theory exists in equations that describe relationship between quantities in a way that cannot be fully captured by simple, visual imagination. As physics continues toward attempts to unify quantum mechanics and gravity, the reliance on mathematics becomes even more extreme. Proposals such as string theory or loop quantum gravity describe reality using highly abstract mathematical frameworks. In these frameworks, the basic building blocks of the universe are not objects in space, but mathematical structures such as vibrating strings, spin networks, or higher dimensional geometric objects. These concepts are far removed from everyday intuition and exist primarily as mathematical descriptions rather than physical pictures. Even experts rely more on mathematical consistency than on visualization. A theory is judged not by how easily it can be imagined, but by whether its equations produce consistent results and match observations. If the mathematics works, the theory is considered meaningful, even if the physical interpretation is not fully clear or easily visualizable. This shift has a profound implication. The deeper we go into reality, the more we are forced to abandon intuition and rely on formal structure. Intuition is shaped by human-scale experience, but the universe operates at scales and conditions far removed from that experience. Mathematics, however, is not limited by scale or sensory perception. It provides a language that remains consistent, whether describing atoms, stars, or the entire universe. This does not mean intuition becomes useless. Instead, it means intuition must evolve. It becomes trained by mathematics rather than replaced by it. Physicists often develop a kind of mathematical intuition where they begin to feel how equations behave without needing to visualize them in everyday terms. But even this higher form of intuition is still grounded in formal structure. What makes this transition so important is that it reveals something fundamental about reality itself. The universe does not appear to be designed to fit human intuition. Instead, it appears to follow patterns that are inherently mathematical in nature. The deeper we look, the more we find that physical reality is not something we can fully capture through images or simple analogies. It is something that must be expressed through relationships, symmetries, equations, and structures. So when we say that the deeper we go into understanding reality, the more it turns into mathematics instead of physical intuition, we are describing a gradual shift in the language of reality. We start with experience, move into models, and eventually arrive at a point where only mathematics remains reliable. And at that deepest level, reality is no longer something we simply picture. It is something we calculate, describe, and understand through the precise structure of mathematical relationships. When we begin thinking about the world in everyday terms, it feels natural to imagine reality as being made of things. There are objects that exist independently: rocks, trees, planets, people, particles. Each of these seems to have its own identity, its own substance, and its own existence that does not depend on anything else. In this view, the universe is like a collection of building blocks scattered across space, each one carrying its own properties, and all interactions happen between these pre-existing objects. This way of thinking works well at human scale. It matches what our senses tell us. You can pick up a stone and feel its weight. You can look at a star and assume it exists as a distant object with fixed properties. You can imagine particles as tiny spheres moving through empty space. This picture is simple, intuitive, and useful for everyday reasoning. But as physics goes deeper, this object-based picture begins to break down. The idea that things exist as independent units starts to lose meaning. What remains consistent across modern physics is not the idea of isolated objects, but the relationships between them. In many of the most fundamental theories, what is real is not the thing itself, but how it interacts with other things. At the level of classical physics, this shift is subtle, but already present. For example, in gravity, what matters is not just that objects exist, but how they influence each other through distance. The motion of one object is defined entirely by its relationship to another mass. Even here, reality is already beginning to look less like isolated objects and more like connected behavior. As we move into electromagnetism, this relational structure becomes clearer. Charges do not simply exist in isolation. Their behavior is defined entirely by how they interact with fields and other charges. An electric field is not something you can separate from its effects. It is defined by what it does to charged particles. Magnetic effects arise only through motion and interaction. The system becomes less about things and more about how things influence each other across space. When we reach quantum physics, the shift becomes even more dramatic. Particles are no longer described as solid objects with fixed properties. Instead, they are described through mathematical relationships that predict probabilities of interaction. An electron is not a tiny ball with a definite path. It is a set of relationships that determine how it will behave when it interacts with something else. Its position, momentum, and other properties are not fixed until they are measured, meaning they do not exist as independent attributes in the classical sense. In this framework, what is fundamental is not the particle as an isolated object, but the structure of interactions it participates in. The outcomes we observe depend on how systems relate to each other during measurement. Reality becomes something that is defined through events of interaction rather than static existence. As quantum field theory develops this idea further, particles themselves are no longer treated as fundamental things. Instead, fields are considered primary. These fields exist everywhere in space, and what we call particles are simply localized excitations or disturbances in those fields. In other words, a particle is not an object sitting inside space. It is a pattern of change within a continuous field structure. What matters is not the particle itself, but the way the field behaves and interacts at different points. This is where the idea of things starts to lose its traditional meaning. If everything is an excitation of a field, then there are no separate objects in the usual sense. There are only patterns in a continuous system, and what we call objects are stable patterns that persist long enough for us to recognize them. At the level of spacetime itself, general relativity continues this shift. Space and time are not fixed containers in which objects exist. Instead, they form a dynamic structure shaped by mass, energy, and momentum. Gravity is not a force acting between objects in space. It is the result of how spacetime geometry responds to energy. In this picture, even space is not an independent stage. It is part of the relational system. This means that the positions of objects are not absolute. They only have meaning relative to other objects. Motion is not defined against a fixed background, but through changes in relationships. Even time is not universal, but depends on how different systems move and interact with gravitational fields. As physics continues toward more advanced and speculative frameworks, such as quantum gravity, this relational view becomes even more extreme. In approaches like loop quantum gravity, space itself is described as a network of relations. What we perceive as distances and volumes are not fundamental quantities, but emerge from connections between more basic elements. These elements are not things in space. They are relationships that define space itself. Similarly, in other modern approaches, the idea of objects disappears entirely at the deepest level. Instead of thinking in terms of particles moving through space, physicists describe the universe in terms of interactions, amplitudes, symmetries, and correlations. These are mathematical relationships, not physical objects. What is real at the deepest level is not what exists, but how existence is structured. This leads to a profound change in how reality is understood. The traditional picture of the universe as a collection of objects gives way to a picture where objects are secondary. They are not the foundation, but the result. The foundation is a network of relationships that give rise to the appearance of objects when observed at larger scales. One way to understand this is to think about how patterns emerge in other systems. For example, a wave in the ocean is not a separate object moving across water. It is a pattern of motion within the water itself. The wave exists only because of relationships between water molecules. If you zoom in far enough, there is no wave object, only interactions between parts of the system. Yet at a larger scale, the wave becomes real enough to track, measure, and describe. In a similar way, modern physics suggests that everything we call an object may be like that wave. Stable, recognizable, and measurable, but ultimately not fundamental. What is fundamental are the underlying interactions that produce these stable patterns. Another example comes from language itself. A word is not a physical object, but a relationship between sounds, meanings, and shared understanding. The word exists only because of the structure of communication between minds. If you isolate it from all context, it loses meaning. In the same way, physical objects may only have meaning within a network of physical relationships. Even identity begins to shift in this picture. An electron is identical to another electron, not because each has a separate identity, but because they are described by the same underlying structure. What defines them is not individuality in the classical sense, but position within a set of rules and relationships. As this view develops further, reality becomes less like a collection of independent objects and more like a continuously evolving web of connections. What we observe as things are stable patterns in this web. Their properties are not intrinsic in isolation, but defined through how they interact with everything else. This does not mean objects are illusions in a simple sense. It means they are emergent. They are real at the level where we experience them, but they are not fundamental at the deepest level of description. Just as a forest is made of trees, but also something more than just individual trees, reality at large scales is made of patterns that arise from deeper relational structures. So, when we say that at the deepest level reality stops behaving like things and starts behaving like relationships, patterns, and interactions, we are describing a shift in the foundation of physics itself. The universe is no longer best understood as a set of isolated objects sitting in space. Instead, it is better understood as a dynamic system of connections, where what exists is defined by how it relates, not by what it is in isolation. And as we continue to push deeper into fundamental physics, this relational view becomes more dominant, suggesting that the most basic layer of reality may not be things at all, but the structure of relationships from which the appearance of things ultimately emerges. And this leads to the final realization. Everything you call real is consistent, but not necessarily fundamental. Everything you trust as solid is stable, but not necessarily what it truly is. And everything you assume exists independently may only exist as part of something deeper that has not yet revealed its true form. Because the more science progresses, the less the universe behaves like a collection of objects, and the more it behaves like something we are still learning how to interpret. And that leads to one final thought. Maybe the universe was never meant to look like what it appears to be. Maybe what you call reality is just the closest translation your mind can survive of something far more complex underneath it. And if that is true, then nothing is what it seems. Not even for a single moment.